being the last session, you must really love multi-party computation. It is my pleasure to introduce the speakers of this session. And the first speaker will be Safir Freizet. She will be talking about robust additive randomized encoding from I/O and pseudo nonlinear codes. Okay, so the floor is yours.
Okay, so thank you for the introduction. Okay, so this is a joint work with Nir Bitansky. Okay, so let's begin. Okay, so a basic paradigm in secure computation is to reduce the secure computation of a generally complicated function to securely compute a simpler function. Okay, so last year in crypto, Alevi, Shai, Kushilevitz, and Rabin took this idea to the extreme, and they asked, can we go as low as simply computing the addition function? Okay, and therefore they introduced the notion of additive randomized encodings, or R in short. Okay, so what are R's? Okay, so as in multi-party computation, we have a public function f over k inputs, and we also allow public parameters. And there are k parties, each having a secret input to the function. And there is a decoder server that wishes to learn the value of the function f of x. Okay, and now in R, we also assume that we have a trusted encoder that takes as input k encodings and outputs their sum. Okay, so now the parties can each can locally encode a value that depends on its original input. All the parties can send the encodings to the trusted encoder, which can then send the sum of all the encodings, f hat, to the decoding server, which then uses the sum in order to compute the value of the function f. Okay, and the sum is over sum abelian. Okay, and we want to maintain, to guarantee, correctness and security, very similarly to the notion in multi-party computation. So correctness just means that the value y equals actually equals to the value f of x, and security means that the decoding server doesn't learn anything else about the private inputs of the parties. Okay, so why do we care about R? Why is it interesting? So in one word, simplicity. So addition is really the simplest function one could think of. And we also mentioned, actually Levi et al. Already showed it in their paper, that this notion can be realized in the shuffle model, where parties are allowed to communicate through anonymous channels. Okay, so in this model, the parties can just send messages to the decoder over anonymous channels, and the decoder can take all the messages and learn the sum of all the encodings from the messages and the sum only. And then it can use the sum as before. Okay, so additive randomized encodings yield non-interactive multi-party computation in the shuffle model without correlated randomness nor public key infrastructure. Okay, so let's discuss the security notion of R. And I am first going to introduce the simple notion where we only assume that the decoding server is corrupted. Okay, so intuitively, we want to argue that the decoding server only, whatever it learned in the execution of the party, it could learn from the value f of x, meaning that it didn't learn anything else about the private inputs of the parties. And we formalize it using a standard simulation security notion. Okay, but in this talk, we are going to focus on a stronger notion of security called robust R, which Alevi et al. Presented also in their paper. And in this notion, we now assume that in addition to the corrupted decoding server, there are also corrupted parties who collude with the server in order to learn information about the inputs of the honest parties. Okay, so note that there is an inevitable attack in this scenario because the adversary can always learn the sum of the encodings of the honest parties, and it can just use it and plug in other inputs to learn the residual function where the inputs of the honest parties are fixed. Okay, and therefore to define security here, it's natural to use a virtual black box security notion where the simulator has an oracle access to the residual function of the honest parties fxh. Okay, but unfortunately, this notion is a bit too strong. Okay, so actually, Levy et al. Showed that robust R implies obfuscation. Okay, so already two-party simulation secure robust R implies virtual black box obfuscation, which is impossible to achieve in a non-idealized model. Okay, and instead we're going to focus on a weaker notion of security called the indistinguishability security. Okay, so in this notion, we want to guarantee that for every fixed inputs for the honest parties, X and W, with the same residual function, the view of the adversary is going to be indistinguishable between the two cases. Okay, so this notion is weaker than a virtual black box simulation security, but it's still pretty strong, and it already implies I/O. And also, we are going to use I/O when we're going to construct a robust R later in the talk. Okay, so let me give you a quick overview of known results from the paper of Levy et al. From last year. Okay, so they showed how to construct information theoretic robust R for a few functions, or max, and a few more. They also showed how to construct computational non-robust R for all efficient functions from standard assumptions in bilinear groups. And they also showed how to construct simulation-based robust R for all efficient functions in the ideal obfuscation model. Okay, so we said it's not possible, but in an idealized model where we can treat functions as black box, it's possible. Okay, so they mentioned in their paper several open questions, and one of them, and the question we are going to focus on this talk, is can we construct indistinguishability based robust R for all efficient functions from I/O and standard cryptographic assumptions, and of course in the plane model. Okay, so our result is a positive answer to this question, and we are going to construct indistinguishability based robust R from I/O and a new primitive we call pseudo-nonlinear codes. And we also show how to construct this new primitive from either LWE or DDH. And we also get as a bonus feature that our robust R is succinct. Okay, so these are the results. And now let me explain what we mean by a succinct robust R. So this is the picture as before. We have the K parties, the trusted decoder, and the decoding server. But now we allow the parties to split their encodings to two parts. Okay, so GIs are going to be group elements, and ZI are going to be non-interactive parts that the parties are going to send directly to the decoding server. Okay, and in succinct RAR, we demand minimal communication complexity, meaning that the length of the security parameter is going to be proportionate, of the group elements is going to be proportionate to the security parameter, and the length of the non-interactive parts, ZI, are going to be proportionate to the size of the input xi. And in particular, those sizes are independent of k and of the complexity of the function f. Okay, and we also get here that the trusted computation, the part of the summation of the group elements, is as minimal as one could possibly hope for. Okay, so now let's dive into the construction itself. And as a warm-up, we are going to consider the ideal obfuscation model. Okay, so here is an idea of how to start to think about constructing a robust R in the ideal obfuscation model. Okay, so here the public parameters are going to be structured and are constructed K public keys and an obfuscated program P, which does the following. So it gets as input K encryptions. First, it decrypts all the encryptions using the secret keys that are hard-coded in the program. And then it's going to compute the value of F of the messages that are underneath the encryptions. Okay, and now the parties can just encrypt their private inputs, send those encryptions directly to the decoder, and the decoder can use the obfuscated program in order to calculate the value of the function. Okay, but as you could guess, this construction is not secure, and we really didn't use the trusted part here, so it couldn't be secure. But the problem we get is that an adversary could just fix a strict subset of the encrypted messages of some of the honest parties and plug in whatever he wants on all the other inputs and learn information beyond the residual function of the inputs of the honest parties. Okay, so in order to fix this problem, we're going to use the trusted encoder in order to somehow glue together all the honest parties. Okay, so how is it being made? So now every party is going to sample a group element GI in addition to its original input, and it's going to encrypt both GI and its original input and send the encryption directly to the decoder. And it's also going to send the group element to the trusted encoder, which is going to send the sum of all the encodings to the decoder. Now inside the program, inside the obfuscated program, we also added an additional stage, the sum check stage. And the obfuscated program is going to output the value of the function f only if the sum check stage passes. Okay, meaning that if an adversary tries to change a strict subset of the honest parties, it would not be easy for it to do so, because it somehow needed to guess the inner group elements inside the encryptions. Okay, so we also know that we need to use here non-malleable encryption, so an adversary would not be able to just change the inputs X's underneath the encryption and keep the group elements as they are. So using CCA to secure encryption would be just enough. And this model is already secure in the ideal obfuscation model. Okay, but okay, of course we don't have an ideal obfuscation. We want to construct robust R from IO, and just a quick reminder. As opposed to the ideal obfuscation model, where we can take every circuit that we want and just use it as a black box, in IO we don't have this mechanism. Instead, what we have is a guarantee that for every two circuits with the same functionality, they are going to be indistinguishable under IO. Okay, so this notion is of course weaker than the notion of ideal obfuscation, and therefore it's natural that we are going to tackle some problems when moving to IO. Okay, so the first problem that raises in our construction is that in general, CCA2 public key encryptions are not necessarily IO friendly. Okay, but this is a problem that has already been handled before in the literature. And we're just going to use a standard technique where which is called, the solution is to use an Young style double encryption with a statistically simulation sound non-interactive zero knowledge, where we encrypt each message by using two different keys, the left and right keys, and by adding a proof that the encryptions encrypt the same message. Okay. Now the second problem is more unique to our case, and it's a bit more technical, but let me try to simplify the problem. Okay, so just a reminder, we are fixing two inputs for the honest parties, A and B, for which the residual function is identical. And our goal is to show that these two distributions are indistinguishable between the cases. So morally, we need to replace the encryptions of A with the encryptions of B. Okay, so generally speaking, we are doing the sequence of I/O hybrids while using the Naor-Yung paradigm from before. And then the problem we tackle is the following. So we have two programs that we want to argue that under I/O they are indistinguishable from each other, and for that we need the programs to be functionally identical. Okay, but the problem raises up is that if there is a strict subset of inputs of the honest parties for which the residual function is not identical, then the functionalities are different. Okay, so as opposed to the case of ideal obfuscation, where if we have two functions that are not identical, but it's hard to find where they're not identical, then we can still argue that their black box, in a black box manner, they are indistinguishable from each other. Again, if it's hard to find the place where they are not identical, but in I/O we cannot argue that. We need functions to be identical to argue that under I/O they are indistinguishable. Okay, so we need to really make sure that these functionalities are actually identical. Okay, and in order to get that, we are going to replace the group element GI with pseudo-non linear codes encodings, G hats. Okay, and what do we mean by pseudo-non linear codes? We mean encodings that are, first of all, homomorphically additive, so we can still do the sum check stage. And importantly, these codes admit fake encodings for which subset sums evade the code. The fake encodings are indistinguishable from valid encodings. And we show in the paper how to construct them from either LWE or DDH. Okay, so to conclude, we showed how to construct robust additive randomized encodings from I/O and standard cryptographic assumptions in a non-idealized model. And still there are many open questions regarding a robust R and R more generally. And I mentioned them here, a few examples of a few interesting questions. So first of all, in terms of a robust R, it's very important maybe to try to construct robust R with simpler public parameters or maybe with no setup at all, because the public parameters we have here are pretty structured. And also maybe it's an important question to know if there are assumptions lighter than I/O for limited classes of functions maybe. Okay. And there are also many open questions regarding non-robust R, and also you can look at the paper of Alevi et al. From first year to look for more interesting questions. Okay, thank you very much.
Thanks a lot, Safir. Do we have any question? I'll ask a quick question while the next speaker sets up. But maybe so you said that you need this additional trusted encoder to sum over these G group elements values.
Again, can you repeat it?
You need this additional kind of trusted decoder to sum the G values. Like,
yes.
So is this something you get rid of at some point, or like you use it for synchronous? Like, I don't understand if in the final result you still need to assume the existence of this semi-honest decoder, let's say.
Well,
the one where you sum all over this G.
You mean like, wait, 1 second? 1 second, maybe I'll go back a bit slow.
first.
You mean, yes, where,
Yeah.
okay. Can you repeat?
Yeah, do you need, like, if I understand correctly, you need a trusted kind of additional party that does the sum of these group elements?
Yes.
So do you still need that in your final result, or you?
Yes. Okay, of course. We still need, we still need the trusted part. And yes, but it can be, as I said, like in the beginning, it can be realized in the shuffle model, or you need someone like to trust to make this calculation for you. Yeah.
Okay. Thank you very much. Thanks. Okay. Again. All right, so the next talk will be on improved alternating moduli PRFs and post-quantum signatures. And our speaker will be Guru Vamsi Policharla.
Okay.
Whenever you're ready.
Okay. Cool. So today I'm going to be talking about improved alternating moduli PRFs and some new post-quantum signature schemes that you can come up with as well. This is joint work with Naveed, Srini, and Peter. Okay, so when you're trying to design crypto primitives, there's two broad approaches that you would take. So the first one is what I would call provable security. And the second one is a heuristic approach. So what do I mean by provable security? You come up with your construction and you're going to reduce it to the hardness of DDH, LPN, or one of these standard assumptions. On the other hand, with heuristic constructions, you're just going to write down your construction and say, okay, this is secure because I threw a bunch of attacks at it. It resisted it, and so that's why it's secure. Examples of this include AES and SHA, and there's good reasons to take the heuristic approach because these constructions are designed to be fast and performant. But one downside is that the ones based on provable security are often simpler to describe, and there's like a very simple assumption that you try to attack. Whereas with heuristic constructions, the circuit, it's like, the construction itself is so complicated to explain that, it makes it even harder to cryptanalyze. And another downside is that if you're trying to do distributed protocols or maybe prove them in ZK, the heuristic constructions are generally much more expensive. And sort of the reason is because with these DDH or LPN style assumption-based constructions, you can usually come up with protocols that are black box in the underlying algebra, and that's sort of what makes them all the more efficient. Okay, but in light of these trade-offs, we can ask the following question, which is, can we have a fast but simple to describe crypto primitive that are also MPC and ZK friendly? So the alternating moduli paradigm was proposed for this exact reason. It came out in 2018, and the goal was very simple. We want to build simple but shallow MPC-friendly crypto primitives, things like one-way functions and PRFs. So the one-line summary of this entire paradigm is, you just put alternating linear functions over two different fields. And if you set the sizes correctly, they give you a one-way function or PRS. That's it. This linear property is really nice for MPC or ZK because all of these operations come for free essentially. And sort of the only nonlinear component in these constructions is going to be this alteration between when you switch over from one field to the other, and that's sort of going to imply the number of rounds of communication you need and so on. Okay, but you look at this, you're like, there's so much structure in this, right? It's all just linear. There's like this one nonlinear part. Why do they resist cryptanalysis, right? And the short answer is that if you represent this entire function in a single field, turns out it becomes like a really complicated deep circuit. But it has a nice enough structure that you can represent it as like just two alternating functions over different fields, and that's really great for MPC. So you get the best of both worlds. Okay, so I told you about the paradigm. What did they look like? So in 2018, there was a weak PRF that was proposed, and this is it. This is a PRF. So K is a secret key. Oh, sorry. X is a input vector over bits. K is a secret key matrix. And whenever I write this dot subscript 2, I mean operations over F2. And whenever I write dot subscript 3, it's operations over F3. So the way you would evaluate it is you would just come up with your input, and then you would sample a random matrix K. And then at this point, you're going to do a mod 2 to mod 3 switch. So what that means is if you have bits, they just go to 0 or 1. Nothing goes to 2 and F3. And that's it. So the matrix sizes kind of look like this. This is a weak PRF. Also, I didn't define weak PRF, so it's just going to be look pseudo-random when you choose uniformly random inputs, but otherwise, you don't get any guarantees. Okay. So you can also, pick K to be structured if you want faster evaluation. There was a little bit of cryptanalysis done, but nothing crazy. You could just increase the parameters a little bit and fix these constructions. And there's a couple more variants as well that look very, very similar. And there's also a one-way function that was proposed in 2021. So instead of the secret key matrix, you just have like an expanding matrix A, and your input is going to be a vector X. And the claim is that if I just sample a random input and give you this output Y, it's hard to find an X such that this equation is satisfied, right? And these are sort of what the one-way functions look like. It's just random matrices A and B, and that's your random input X. Okay, so what can you do with these one-way functions and PRFs that we came up with, right? So one thing is, if you believe that these are also post-quantum secure, then you could build efficient post-quantum signatures. So I'm going to briefly go over MPC in the head, which is the proof system that we're going to use to build these post-quantum signatures. So all it says is, you can convert an MPC protocol that you have into a zero-knowledge proof. So let's say this is your set of parties running an MPC protocol to evaluate the function f, and you want to convince someone that you know some input w such that f of w equals some claimed y. So in the MPC protocol, each party has a view which contains their inputs, randomness they use, and any messages they sent or received. And let's say this is the prover and the verifier. So what the prover is going to do is run this MPC protocol in its head. And then you're going to commit to all the views of these parties. And then the verifier is going to say, okay, reveal some subset of these views. And the prover is going to send over these views along with the proof that he did the opening correctly. And then the verifier is going to check, okay, are these views consistent? Do they all make sense? And the ZK property of this proof system is going to come from the privacy of the MPC protocol. And soundness is sort of going to come from the fact that if the prover didn't know a valid W, one of these views is going to be inconsistent, and the verifier is going to open one of those views with some non-negligible probability. Okay, so that's what MPC in the head is. Okay, so how do you build signatures given a one-way function, right? There's a very simple recipe. So you have your one-way function f, and all you have to say is, okay, sample a random input to it. That's going to be your secret key, and the output is going to be your public key. And the signature is just a proof that you know this secret key, and the message is going to be a tag in the NIZK. That's it. So the 2021 paper, like I mentioned, introduced this one-way function in the alternating moduli paradigm. And what they got was signatures around 10 kilobytes, right? So they used this off-the-shelf MPC in the head compiler called KKW18, and they got 10 kilobytes. So very recently, last year, there was a paper that said, okay, look, you can actually use AES with a custom proof system. They designed it very carefully to get really tiny signatures, and it's you can get around 5 kilobytes, right? So in light of this result, this 10 kilobyte number is really unsatisfactory, right? Because you design this one-way function to be crypto friendly, and yet you're like 2x larger than like AES, which is probably a very crypto unfriendly one-way function. So the question that we asked is, can we do any better with a custom proof system designed for the alternating moduli one-way function, right? Can you bridge this gap? Okay, so if you wanted to design a proof system for this one-way function, this is what you would prove. This is the relation. So again, linear operations are free, so we don't really have to worry about these A and B matrices. The only thing you really have to worry about is this F2 to F3 map. That's the only nonlinear thing happening, and that's sort of where the proof size comes from. And there's a very simple way to do this. So if you're given correlations of a random bit over mod 2 and mod 3, and you want to convert shares of your message M over F2 to shares of it over F3, all you have to do is reveal M XOR R, and then just compute this equation. Plug in the various test cases, and then you'll see that is correct. Okay, so the 2021 paper, built this MPC in the head protocol for this alternating modular one-way function, and we'll go over it, and we'll try to see where the issues are, and where we can improve it, right? So the first step is going to be, you have these MPC in the head views of each party. which contain shares of the input X and shares of these random correlations. And that's all you need to carry out the MPC in the head protocol. So you're going to send them over, but these are going to be commitments. But there's an issue, which is these correlations sampled by the prover could be malformed. In particular, if you choose them carefully, you can actually create fake proofs, basically that you know a valid input X, but it's just not sound. So what the verifier is going to do is engage in a cut and choose protocol. He's going to say, okay, open up some of these correlations. I'll check that they're correct, and if that passes, I have some guarantee that the rest of them are correct. And then you just execute the online phase of the MPC in the head MPC protocol, and then you commit to their views, and then reveal some subset of these views. Okay. And the total size, like I mentioned, was between 10 and 13 kilobytes. But if you go and look at the cost estimate, right, you'll see that this cut and choose part is just so expensive. It's like 5 to 7 kilobytes of the proof size. And in light of this, you can ask, can we actually just avoid this cut and choose, right? Is there a way to reduce the size and so on? And it turns out you don't even need a cut and choose at all. All you have to do is demand that the prover permutes the correlations before using them. So let's get into what this means, right? So in the first step, when he sends over these xi and ri pairs, what he's saying is, okay, for the ith bit of this intermediate vector, I'm going to use the ith correlation to sort of do this mod switch. And in this situation, if you choose your randomness in a malicious way, what you can do is you can sort of cheat in this mod conversion protocol, and that's going to allow you to eventually end up at y. But now what the verifier is going to say is, okay, first commit to all your randomness. You could commit to them maliciously. They could be fully malformed. But the fact that I'm going to demand that you use a permutation of this, which means for the ith position, I'm going to demand that you use something else, is going to mean that the places you try to cheat are not going to quite align. So if you wanted to cheat in the 5th position, you might have created some malform correlation for that particular position, but now I'm going to ask you to use a completely different correlation there, which might be honest, might be cheating in a completely different way. And that's sort of where the soundness comes from. But you have to really be very careful with the analysis, and it's also going to rely on very special properties of this function. So this is not something you can just do for pretty much any function. And similar techniques were used in a Eurocrypt paper last year, but the exact details of the analysis are quite different. Okay, and the nice part about this is the permutation is just going to be free, right? All you have to do is sample a Fiat Shamir seed and say, okay, this is what I'm going to use to determine my permutation. So this cut and choose step completely disappeared, and we're saving essentially 5 to 7 kilobytes. And that is basically how you drop down from 10 to 13 to 4 to 5 kilobytes. So I've listed a bunch of assumptions and sort of the best known signature sizes from these assumptions. The fast column denotes a fast prover but larger proof size. The short column denotes a slow prover but a shorter proof size. Okay, and the alternating moduli one-way function is not blowing everyone out of the water, but at least now we're competitive with all the other known constructions. Okay, cool. So we also propose a new weak PRF. Okay, so this was sort of what was there in the previous 2018 paper. And if you're trying to evaluate this weak PRF in MPC, let's say in a distributed setting where let's say you have shares of the key, or maybe one party has the key and one party has the input, you need O of lambda square multiplications because this is just a matrix, right? And you can reduce the communication by using circulant matrices and some clever PCG tricks. But the problem is your work is still superlinear in the security parameter. And when you run these or implement and you sort of benchmark, you'll see that at even moderate network speeds, like 50 megabytes per second, you'll end up realizing that you're bottlenecked by the computation, not the communication. And so we would really like to lower this work as well to get really good end-to-end performance. So this is our new weak PRF. Is it secure? I don't know. But we did a bunch of cryptanalysis. Nothing seemed to work. So here's a candidate. So instead of having a matrix times a vector, what we said is, okay, just sample a secret key vector and just take a Hadamard product with your input. So all you're saying is some of these coordinates are going to be zeroed out in the input. I'm not going to tell you which one. And I'm just going to evaluate this A times B on top of that, right? And also we choose these A and Bs to also be kind of structured to have linear time encoding, which is also going to speed up the evaluation process. So really aggressive, but if it breaks, Okay, that's fine. We learned something. If it didn't, well, you have a really fast weak PRF. Okay, so these are sort of the dimensions of it. This is sort of how the new weak PRF that we propose looks like. Very similar to what it was before, except you have this Hadamard product in the beginning. Okay, so in the remaining time I have, I'm going to quickly summarize, or at least give you a high-level idea of how we implement an OPRF protocol for this. So what is an OPRF? Your PRF has two inputs, your key and X, which is the point you want to evaluate your PRF on. It's going to output some Y. So let's say one party has the input and the other party has the key, right? So what we want is an interactive protocol between these two parties such that the party with the input is going to get the output of the PRF. The party with the input shouldn't learn anything about the key, and the party with the key shouldn't learn anything about the input or the output. Simple 2PC. Okay, so let's go back to our new weak PRF. This is what it looks like. And there's only two nonlinear steps here that you really have to handle, which is this Hadamard product and this F2 to F3 map, right? So to implement this Hadamard product, the first observation is that this key K is actually going to be reused across all of your evaluations. So it's going to stay the same across all of your evaluations. And what this means is you can actually reuse, in some sense, the OT correlations across all of the evaluations. It's not quite the same as just use the same things. There's sort of like a trivial OT extension protocol if one party's inputs is the same. And that's sort of how you get this reusing behavior. And so you do a one-time setup per client, and then you can forget about it. So you never need to do any more interaction to sort of multiply these K Hadamard product with X. Okay. And we propose two approaches to implement this mod 2 to mod 3 conversion. The first one is OT-based, so concretely much less communication, but you're going to start consuming OTs every time you do this mod switch. So you'll have to set up these OT correlations again. The second one is a garbling-based. It's going to involve more communication, but you don't need any setup for this. In particular, if you want secret shared outputs, so after the initial setup of these K Hadamard product with X, you can actually just get it in one round. So just one message going to one side, and you can get a secret shared output. So we implemented our schemes. These are the numbers. So the one thing that I want to highlight is, if you look at the DDH-based construction, the DDH-based OPRF, the computation time is going to be much, much worse than any of the alternating moduli PRF-based constructions. And the communication, at least for the OT-based protocols, is going to be like maybe 2x worse. So in practice, you'll probably be better off using these if you have many, many OPRF queries going around. In the garbled circuit-based approach, there's a 0.0 plus something because we don't need any time in the setup. And you need 4 microseconds to actually evaluate the garbled circuit and get a secret shared output. Yeah, okay, so good. Okay, so before I conclude, I sort of have a wish list in this space, right? If I got 3 wishes, what would I do? The first one is more cryptanalysis, right? This came out in 2018. There's only like 1 cryptanalysis paper. We don't really have much more. We did something. I don't know if it's secure, but we tried our best. So one thing I want to highlight is, there might be a better way to analyze functions over alternating fields, right? It's not just that you have to write in one field and, okay, I apply whatever cryptanalytic techniques and it doesn't work. Also, what about if you were given a quantum computer, right? Does this make the problem easier? We would also like some new primitives, right? So we have one-way functions and PRFs. What about hashes, right? Or what about even a random oracle? And finally, I'd like to see better protocols because we've only started just scratch the surface of optimizing these protocols. It would also be nice to see much better implementations, exploiting like AVX and so on. Yeah, thank you for listening.
Thanks a lot, Guru. So, do we have any question? So, in the interest of time, I would say let's thank Guru again and let's welcome the next speaker. Okay, so the next talk is about game theoretically for distributed sampling, and the speaker will be Ki Wu.
Oh, okay.
feel free to start when you're ready.
So yeah, thank you for coming in this last session. So I'm very happy to share this work, Game Theoretically Fair Distributed Sampling. This is a joint work with Aravind from University of Sydney and Pratik from University of Utah. Okay, so before the conference, we need to decide who will come present this paper. Should I? All right. Aravind is in Sydney, so he's not coming. It's either Pratik or me. We both really want to come because we want to enjoy the beautiful beach at Santa Barbara. So we say, okay, let's toss a random coin. If the outcome is zero, Pratik will win and he will come. If the outcome is 1, I will win and I will come present the paper. You already see me here, you know the result, but let me tell you what happened. As cryptographers, we say, let's do Blum's coin toss protocol. Okay, we each commit to a random bit, post the commitment on some public bulletin board, like blockchain, and we each open our random bit. Pratik's bid was 1 and my bid was 0. So the outcome is just the XOR of these 2 random bits, which is 1. So I win, and here I am. However, Pratik is really smart, and he's a strategic guy. He can wait for me to open my bid first. He sees it's 0. Now he knows, okay, if he opens his commitment honestly, he's gonna lose the game. So what if he refuses to open his commitment? Then in this case, I will just automatically win. So the outcome, it would still be 1. So in this protocol, even if Pratik does not follow the protocol honestly, he cannot gain any benefit. So formulating a coin toss protocol, our goal is to toss a uniformly random coin. And here we care about 2 properties. Correctness. If everyone behaves honestly, then the output should be a uniformly random coin. We also care about fairness of the random coin. So the notion that has been considered in classical cryptography literature is called strong fairness or non-biasability. It requires that a strategic player should not be able to bias its outcome towards any direction. Unfortunately, this has shown to be impossible by Cleve in 1986. For any polynomially many rounds 2-party coin toss protocol, a strategic player always have a strategy to bias the outcome. Even in the Blum's coin toss protocol we just saw, Pratik can always bias the outcome towards 1 by intentionally losing the game. But a rational player would not do this. So Blum's coin toss protocol actually achieves a weaker notion of fairness, a game theoretic flavor of fairness. There we are guaranteed that even if Pratik does not follow the protocol, he cannot gain any benefits. So this notion was first formally proposed by Cheng et al. In their TCC 2018 work. It is called game theoretic fairness. It guarantees that a strategic player should not be able to benefit themselves by deviating from the protocol. Okay, so now we've seen a 2-party binary coin toss that achieves this game theoretic fairness. What about a more general case? What about multi-party, multi-sided coin toss? Okay, multi-party, multi-sided coin toss, players come together and they want to decide some uniformly random coin. Let's say they want to do 4-sided coin. Each player has a publicly known preference. So some of them prefer 0, some of them prefer 1. And we call this who prefer 0 as 0 supporters, those who prefer 1 as 1 supporters, and so on. At the end of the protocol, we get an outcome, which is either 0, 1, 2, or 3. Okay, so now a player gets utility 1 if the outcome matches its preference, or 0 otherwise. Here, some of the players may form a coalition, and their goal is to maximize their joint utility, which is the sum of the coalition members' utility. For example, if the outcome is 2, then this coalition gets utility 2. Now for multi-party, multi-sided coin toss, let's say we want to do M sides. We again care about the 2 properties, correctness and fairness. Correctness says that, okay, if everyone behaves honestly, the output should be uniformly random M-sided coin. And the game theoretic fairness now is defined with respect to coalition. we hope that any strategic coalition should not be able to increase its expected joint utility compared to honest behavior. So basically, this game theoretic fairness guarantees that the honest protocol forms a Nash equilibrium. So any player is incentivized to follow the protocol honestly. Okay, one question here might be that, why should we care about this game theoretic fairness? Why not just stick to strong fairness? Well, we know that randomness is widely deployed in many decentralized applications, lotteries, leader elections, online games, et cetera, et cetera. And in all these applications, we care about the fairness of the randomness we used. But strong fairness is only possible if we have honest majority. Unfortunately, in many decentralized applications, it does not make sense to assume honest majority. It is possible that the adversary creates many pseudonyms and control a majority number of pseudonyms running this randomness generation task. Such kinds of attack has happened in real world. There are people who are creating many pseudonyms and juice value from the Solana blockchain. So in practice, we may not always assume honest majority in decentralized applications, yet we still want to achieve some meaningful fairness guarantee. So that's why we turn to this game theoretic fairness. Okay, now you may ask, okay, then can we achieve game theoretic fairness against corrupted majority? So people have studied game theoretic fairness for some specific tasks. For example, Chen et al. And one of my previous work with Asharov and Shi studied game theoretically fair multi-party binary coin toss. There we give a complete characterization on the size of the coalition we can tolerate. And indeed, we show that we can achieve game theoretic fairness against corrupted majority. The formula there is quite complicated, so I omitted on the slides. In their follow-up work, Chong et al. Also studied leader election, and they present a leader election protocol that achieves game theoretic fairness against any sized coalition. So now we've developed a quite complete understanding for binary coin toss and for leader election. But what about the whole middle space? The whole middle space of multi-sided coin toss is unknown to us. What does the landscape look like? Exactly where should we draw this line between feasibility and impossibility? So in this talk, we answer this question. In this work, we give a protocol for multi-party, multi-sided coin toss that achieves game theoretic fairness against corrupted majority for any polynomial m. We also extend our protocol to a broader range of tasks, distributed sampling, where players want to generate some randomness from non-uniform distribution. And for these kind of tasks, we also give game theoretically fair protocol that tolerates corrupted majority. We also give an impossibility result and show that our protocol is nearly optimal up to a constant factor for a broad range of parameters. So in the rest of this talk will be split into two parts. So the first part, we will talk about composition. Usually when we talk about multi-sided coin toss, our first thought is to compose using binary coins. Unfortunately, I will show you with a concrete example that for game theoretic fairness, composition, direct composition does not work. And due to this reason, we have to come up with a protocol from scratch. And I will show you our protocol after we see why composition does not work, and I will show you how we achieve game theoretic fairness. Okay, so why composition doesn't work? Let's say we want to do a four-sided coin among these 6 players. Okay, naive idea is to say, let's do 2 binary coin toss. If the 2 binary coin give us 0, 0, we get outcome 0. If it's 1, 0, we get outcome 2. Okay, very direct mapping. Now for simplicity, let's write the preference of the players in these 2 bits form. Okay, so this is the 0, 0 supporter, 0, 1 supporter, 1, 0 supporter, and 1, 1 supporter. So clearly each player has a preference of the first coin and a preference of the second coin. Okay, now let's run our first binary coin toss. We're going to let those players who prefer 0 of the first coin play against those who prefer 1 for the first coin. They will run a game theoretically fair binary coin toss to decide the first binary coin. Similarly, we will let those who prefer 0 for the second coin play against those who prefer 1 for the second coin. They run another game theoretically fair binary coin toss to decide the second coin. Okay, so very direct composition. But this protocol does not work. It does not tolerate half-sized collision. And let me show you why this is the case. Let's consider this collision. It controls all the 0 supporters and all the 1-0 supporters. Okay, they will adopt the following strategy. First, they behave honestly in the first coin toss protocol. And then, if the first coin is 0, in the second coin toss, they will bias the outcome towards 1. I claim that first, this coalition is definitely able to perform this attack, because first, they control half-size coalition, so by cleave, they can always bias the outcome. Game theoretic fairness guarantees that this coalition cannot bias towards their preference, which is 0 in the second coin toss, because they control more number of players preferring 0 for the second coin compared to the number of players preferring 1 in the second coin. So they must be able to bias the outcome towards 1. And this strategy strictly increases this coalition's expected utility, because when the first coin equals to 1, this coalition actually prefers, when the first coin is 0, this coalition actually prefers 1 of the second coin, because they control a 0-1 supporter, but no 0-0 supporter. Okay, so this coalition can perform this strategy, and they can increase their expected joint utility. So this protocol does not achieve game theoretic fairness against half-sized coalition. In general, this direct composition does not work because we cannot deal with this inconsistency of coalition's preference. In our example, it seems that the coalition prefers 0 in the second coin toss. But in fact, when the first coin, conditioned on the first coin being 0, this coalition's preference changed. And we cannot deal with this inconsistency of coalition's preference in each single instance of the binary coin toss. And that's why composition does not work for game theoretic fairness. Okay, now this failure of composition implies that we need to build our protocol from scratch. And now let me show you a protocol that works for these 6 players that tolerates 3-sized coalition. For simplicity, I would only talk about the protocol against semi-malicious coalition. So how does the protocol work? We split them into 2 groups. First group is the 0 supporter who prefers the least preferred outcome. Second group is the remaining players. Okay, we first let the 0 supporter commits to a random M-sided coin C0 and post the commitment on the public bulletin board. And then for the second group, we let them do a 3 out of each player in the second group do a 3 out of 5 Shamir secret sharing to share a random M-sided coin. And for simplicity here, I directly use C1 to denote the sum of their coins. Of course, this sum is sum modulo M. After they share the coin, we let the 0 supporter reveal its value C0 and post the value on the public bulletin board. And also the second group, they will run the reconstruction of Shamir secret sharing to reconstruct the value C1. At this point, if everyone behaves honestly, we will see 2 values on the board. So we just output the sum of the 2 values. Of course, modulo M. But what if the 0 supporter refuses to open its commitment? In this case, we just still let the second group reconstruct their value C1 and use C1 as our outcome. But what if the coalition controls 3 players in the second group, they abort during the reconstruction, and they fail the reconstruction of C1? In this case, what should we output? Can we use C0 as the outcome? The answer is no, because by the time the coalition decides whether they want to fail the reconstruction of C1, they already see the value C0 on the board. So if they like, they will say, okay, if I like C0, I will abort. If I don't like, I will continue my reconstruction. We don't want that to happen. So if the reconstruction of C1 fails, we will directly output 0 as a punishment. So now let me explain why it satisfies fairness against collision of size 3. If this collision does not contain the 0 supporter, then C0 must be a uniformly random coin. The key point here is that this collision does not want to fail the reconstruction of C1, even if they don't like the outcome. Because if they fail the reconstruction, the outcome will be 0, which will only make the collision gets utility 0. So they are incentivized to guarantee the reconstruction of C1. So with this guarantee, and the point that C0 must be uniformly random and independent from C1, we get that our outcome C0 plus C1 must be a uniformly random coin. So we're good in this case. If the collision actually now contains the 0 supporter, then even easier, C1 must be a uniformly random coin, and C1 must be successfully reconstructed. Again, we have a uniformly random output. So the key point in this protocol here is really that if the reconstruction of C1 fails, we output 0 as a punishment. So this protocol achieves game theoretic fairness against collision of size 3. And our impossibility actually showed that for this 6 players, no protocol can achieve game theoretic fairness against collision of size 4. So this protocol is actually optimal. So can we generalize? Of course we can. We can actually generalize this protocol to any polynomial M and to any number of players. So without loss of generality, let's say 0 is the least preferred outcome. And for a uniformly M-sided coin, this T is the size of the collision our protocol can tolerate. So the formula here is really hard to parse. You don't need to understand it, but the key point here is really that the landscape of game theoretic fairness is very different from that of strong fairness. Here, the size of the collision we can tolerate not only depends on N, the number of total players, it also depends on the fraction of N0. It depends on the fraction of the players preferring the least preferred outcome. So for better understanding, let me show you a direct visualization. Here we express T, the size of the collision we can tolerate, as a function of N0 and N other, which is the number of other players. Here, this second figure, we just reverse the T-axis for better comparison. So here we can see that for each M, the landscape consists of 2 planes with a smooth phase transition in between. So this is very different from that of strong fairness. And as the number of sides increases, the size of the collision we can tolerate decreases. But for any M, we can still tolerate half or more size collision. Okay, so to wrap up, game theoretic fairness is a notion of fairness that captures incentives of the players. It guarantees that a strategic coalition cannot gain benefit by deviating, and indeed, we can achieve game theoretic fairness against corrupted majority. And another thing here is that the landscape is very different from strong fairness. It really depends on the fraction of the players who prefer the least preferred outcome. And there are some interesting open questions. So the first one is, how do we make this protocol practical? Our protocol for a semi-malicious coalition runs in constant rounds, but the protocol against malicious coalition runs in quadratically many rounds. So is there a way to reduce the round complexity or communication complexity? A more exciting area would be, how do we introduce incentives in other cryptographic primitives? In this talk, we've seen that introducing incentives circumvents impossibility results in randomness generation tasks. So can we introduce incentives in other cryptographic primitives based on the application scenario and get better results? So I'll stop here, and I'm happy to take any question. Thank you.
Do you have any question? Please check if it's on.
Thanks for the great talk. Yeah, I just had a question, like in the modeling of a utility. So like you said, like for a subgroup, like the utility is the sum of utility of everybody.
Mhm.
right? So I was wondering, like, what would happen if I change the utility function of the group? Like, for example, it was the weighted sum of utilities of parties, or if it was maximum of the utility of the parties in the group. Does that make sense? Like, if I change the utility function, what would the results look like?
Yes, yes, that's a very good question. So if we just choose a very simple other kinds of utility function, we just change the one to some other numbers, I think it will slightly change the size of the coalition we can tolerate. But a more general, I think a more interesting case, which I'm actually currently working on, is what if a player can arbitrarily distribute its utility on the possible outcomes? And I think I don't have a concrete answer now, I'm still working on it, but I think that's a very interesting future direction. Yes?
In your protocol, you need to know which player supports which outcome, right?
Yes.
What if you do not know that?
So that's a good question. So I think if the whole protocol has no information of the preference at all, we can prove some form of impassibility result. So I think a more interesting question would be, can we hide the preference of the players?
Thanks.
Any more questions? All right, let's thank the speaker again.
Thank you. Thank you.
Okay. All right, so the next talk will be on scalable multi-party computation from non-linear secret sharing. And Mingyuan Wang will give the talk.
Hello? Hello? Yeah, this is good, right? Okay, yeah. Thanks for the introduction. And thanks to everyone for sticking around. I promise I won't keep you for too long. So I'm very happy to present this work, scalable multi-party computation, but from nonlinear secret sharing. This is a joint work with Sanjam, Abhishek, and Pratik. So this is about MPC. I am sure you all know what MPC is. Here we have a set of parties who collectively want to evaluate some function with their respective private input. Security says that if a set of parties are corrupted, their view should be indistinguishable as if they are interacting with a trusted party in the ideal world. So in this work, the setting we consider is first, it's an honest majority and the information theoretic playing model. So there's no pre-processing. And we will only consider semi-honest adversary. So very basic setting. What is our objective? Our objective here is to try to minimize the overall communication and computation complexity of the entire protocol. And in particular, if the function we are trying to evaluate is modeled as a arithmetic circuit C over some finite field F, we want to achieve that the overall computation complexity to be only in circuit size, meaning field operations. And note that this is an optimal goal because even if there's only one party who's trying to insecurely evaluate the circuit, it needs this much operation. And the MPC protocol that achieves this level of efficiency is sometimes known as the scalable MPC. Here, scalability means that the overall complexity of the protocol doesn't grow as the number of parties in the system grows. Okay, cool. So you might wonder, why do I care about scalable information theoretic MPC? First, most of the practically efficient MPC protocol are in the information theoretic setting. This only involves cheap field operations, but not expensive cryptographic operations. And in particular, if you have an MPC protocol where the total complexity doesn't grow with the number of parties, then you can increase the number of parties without worrying about the total complexity grows. And this has some advantages. For example, as the number of party grows, the average, the workload per party will decreases. And so you can distribute a large computation to a number of many parties such that each party only do a small amount of work. And finally, the honest majority assumption also becomes more reliable in practice as the number of party grows. And finally, many natural applications in the real world does involve many parties. Okay, good. So hopefully I have convinced you that we should care about scalable information theoretic MPC. Now, what does the current state of art looks like? So this is really based on a sequence of very amazing works. And the first result we know is that if you consider some type of structured circuit, for example, a same-D circuit, this is the same circuit that's being copied many times, then the seminal work of Franklin Young shows that we do kind of achieve scalable efficiency. And the recent work by Beck et al. Slightly generalized this work, the Franklin Young's paradigm, to a special family of circuit called highly repetitive circuit. So this is for very structured circuit that has a special structure, we can achieve scalable efficiency. On the other hand, if you consider a general circuit, that is an arbitrary circuit that does not necessarily have any topology structure in it, the seminal work of Demigard et al. Introduced this very nice idea that you can potentially do some circuit transformation that transform a general circuit into some special circuit that has some special structure. And by leveraging this structure, you can achieve some level of scalable efficiency. However, this is still not fully scalable in the sense that it still introduces some polynomial overhead in the logarithmic size of the circuit and the depths of the circuits. And finally, the recent work of Goyo et al. Introduced some techniques called shared transformation that allow us to do, for general circuit, achieve scalable efficiency in the communication. That means the total communication of the protocol is the field, is the circuit size many field elements. But on the computation side, it still has complexity, the number of parties into the circuit many field operations. So the question we ask in this work is that can we build a scalable MPC protocol for general circuit that achieves scalable efficiency in the computation of the protocol in the computational complexity? Okay, so let me state our result. Our result works for any field that is exponentially large, and for any arithmetic circuit over this exponentially large field, we build a scalable MPC protocol among n parties, such that the overall communication and computation complexity measured at the bit level is the circuit size into the logarithmic of the field size f. So notice that here, this number of bit operation is roughly equals to the operation you need for evaluate circuit number of field operations. So the question is how large this field needs to be. In the paper, we prove that as long as the field size is exponential in n squared, the n is the number of parties, then we can prove security. And we also conject that our protocol or some modification of protocol can be secure even when the field is only exponential only in the number of parties. The first quick comment about this result is that unlike previous work who typically measure the complexity as how many field operations all the party needs to do, here we have a bit unusual measure that we have measured things at a bit level. Later in the talk, you will see why this is inevitable for us. The second point is that in our paper, we also extend this to a dishonest majority, assuming a pre-processing model. This is a standard trick in the MPC literature. In the interest of time, I won't talk about it, but I encourage you to look at the paper. And finally, this point was really brought to us by an anonymous reviewer that using existing techniques, you can also get a protocol that achieves similar level of efficiency. But the rough idea is that you can, when the field is large, you can translate an arithmetic circuit into a Boolean circuit. And this circuit will have some repetitive structure, and you can apply existing work on top of it to achieve similar complexity. However, this is not favorable over our protocol because first, asymptotically, still have a few more logarithmic overhead more than what we achieve. Secondly, to transform a arithmetic circuit into a Boolean circuit is quite expensive concretely also. And this is exactly for the same reason why we sometimes prefer arithmetic garbling, even though we already have Yau's garbling for a Boolean circuit. And next, I want to talk about our assumption that the field size is exponentially large. You might wonder this, typically in MPC protocol, we only assume the field is polynomially large. You might wonder whether this is only of theoretical interest or this is practically relevant. And then we argue that sometimes this could be practically relevant. For example, when you are using MPC protocol to compute some cryptographic tasks, for example, the computation of snark generation using MPC, this has been the topic of many recent works, then in those applications, the field size will be exponential in the security parameters. So they are naturally an exponentially large field, and our protocol can plausibly be applied to such computing cryptographic tasks using, for example, 100 to 200 parties, and this could be quite relevant in practice. Okay, good. With that, I will now move to the technical part of the talk, where I want to give you some idea of how our techniques roughly looks like. So recall that we are in the information theoretic setting. So a standard way of doing information theoretic MPC is that you start by sharing the input using synchronous sharing schemes, and then you emulate the circuit gate by gate. For example, you can start with the, if you have an addition gate, you start with the share of the input wire X and Y, then parties can locally emulate this gate by adding up their secret shares to get the secret share of the output wire Z. Typically, if there is a multiplication gate, then after that, you need some communication to do some degree reduction to make the final secret sharing well-formed. Especially in particular, if the Shamir secret sharing, then what usually you need is a degree reduction protocol to make sure that the share of the output wire make it back to degree T, where T is the corruption threshold. Now, to achieve a scalable efficiency for this kind of secret sharing based MPC protocol, there are generally two techniques that has been introduced to achieve scalability efficiency. The first one is called packed secret sharing, introduced by Franklin and Young. And the second one is called batched randomness generation using Vandermonde matrix introduced by Damgard and Nielsen. And to achieve scalability efficiency, you really need both techniques to achieve this. And to give you a one-line summary of what we did in this work is that first, we introduced some dual notion of packed secret sharing, which we call unpacked secret sharing, to mimic the efficiency gain from packed secret sharing. And then for the batch randomness generation, we prove some technical lemma that we call high dimensional smudging lemma, which is make this batch randomness generation technique compatible with the secret sharing that unpacked secret sharing that we introduced. Okay, now let me tell you a bit about both of these techniques. So first, let me try to tell you a bit about why do we need packing to achieve scalability efficiency. So imagine here you have two instances of secret sharing schemes. The first one is sharing X, the second one is sharing Y, a standard Shamir secret sharing. Suppose now I want to emulate an addition gate, meaning that I will ask party to locally add up their secret share to get the secret share of X plus Y. Note that here, all the parties, the collective work that they need to do to emulate this gate is at least n field operations, because each party is doing one field operations. So overall, they are doing n field operations. And that means that you are using n field operations overall to emulate one field operation in the circuit. And this is already an overhead of n if you are just doing this naively. Now, the packing idea is that instead of just using this curve to share one secret X, packing will use this curve to share more than one secret. In particular, you will share order of n many secrets, so X prime and X double prime. And by doing this, when you locally doing addition from all the parties, you are actually emulating order of n many gates in the circuits. So by doing this, you reduce this overhead from order of n to order of 1. So that's the idea why we need packing. However, packing also comes with limitations. The obvious thing is that because you're doing packing, you have to simultaneously emulate many gates at the same time. In particular, you have to emulate order of n gates simultaneously. And this is really not compatible with when the circuit is a general circuit. And that's why all these existing works developed different techniques, try to make the protocol compatible with this packing fact that you have to simultaneously emulating many gates. However, all these works still fell short of achieving computational scalability for general circuit. So let me summarize this, the thing we want to achieve through packing. the crucial efficiencies measure we want to achieve is that we're trying to make the total length of the secret you're sharing over the ratio between the total secret length of the secret you're sharing and the total length of the secret share to be constant rate. Here we're sharing order of n many secret, and the total share is also n field elements. And the drawbacks of packing is that you're only achieving this efficiency in an amortized sense. You are taking n secret and then achieving this constant rate efficiency. So our first idea is that can we achieve this constant rate efficiency not in an amortized sense, but in a non-amortized sense. So we think of this as a dual notion of packing called unpacking, in the sense that you're not packing a number of small secret into a single instance of secret sharing, but you're really unpacking a very, very long secret into smaller secret shares to achieve this constant rate. And if we can do that, then the obvious advantage is that we no longer need to emulate many gates simultaneously. We can just emulate one gate at a time, and that free us from the burden that comes with using packing. So the obvious question is, how can we achieve this? Now, to do this, we use techniques that we recently introduced in last year crypto, which is based on nonlinear secret sharing from Chinese remaindering theorem. So I won't go into the detail of what this secret sharing is, but the main point is that this Chinese CRT-based secret sharing can be used just as Shamir secret sharing, where you do the gate emulation gate by gate, and after every multiplication, you do a degree reduction, just like how Shamir sharing protocol works. Now, I mainly want to tell you why the CRT-based secret sharing can achieve this constant rate in a non-amortized sense. So to do that, just a minimal introduction to what a CRT secret sharing looks like. Here you have a secret from a finite field F, and to share this secret, instead of like Shamir secret sharing, where you re-randomize this secret to be a polynomial, here you re-randomize this secret small s into an integer, capital S. The fact that here you guarantee that this capital S is equal to small s modulo P. Now here comes how you share this secret into different shares. So to do that, you simply pick many different modulus, P1, P2 to Pn, and the share that Pi get is just this integer modulo Pi. And the good thing about CRT-based secret sharing is that you can pick this P1 to Pn arbitrarily as long as they're co-prime. And because of that, we can pick each Pi to be very small. For example, if I pick P1 to be 2, the share that the first party get is just 1 bit. And through this, we can potentially get a constant rate secret sharing where the secret size is comparable to the total length of the secret shares. Okay, good. So now just a few quick comment about these techniques. The first thing I want to say is that this inherently requires that the field size is exponential in n, because each share has to have at least 1 bit. So the total share length has to grow with the number of parties. If we want to achieve a constant rate independent of n, then the secret length should also grow with n. And this is also, as I promised, this is why our protocol inherently has to measure the complexity at the bit level, because here, unlike a linear secret sharing where all the secret shares are in the same finite field, in the CRT secret sharing, every party is working with a different finite field, and in order to compare the total complexity, we have to measure them at a bit level. Okay, good. So finally, the other techniques that we need to use is the so-called batch randomness generation. Recall that we also need to do degree reduction after every multiplication gate. This involves a pair of random marks that we need to use. And note that we need to consume 1 pair of masks after every gate. And to achieve scalable efficiency, we really need this pair to be generated in the efficiency comparable to just one field operation. And ideally, if we could just ask one party to sample this share, then we should get this efficiency. However, on the security side, no party alone should know what this mask is. So we have to accumulate shares from all the parties to generate such masks. Now, in order to do this, there's a very nice trick introduced by Damgard Nielsen, which is called the van der Waals matrix randomness extraction techniques, which says that we can ask all the party each generate one pair of masks and use this some matrix to extract n out of t random masks out of this n total masks. Even if for any t parties that are corrupted, we can guarantee that those n out of n minus t pair of masks we extracted is secure. So here we use the fact that this van der Waals matrix is super invertible, meaning that any n minus t by n minus t submatrix is full rank. Okay, cool. So the key technical barrier that our work faces is that here, the distribution of the secret here are over the integers. And in order to use the van der Waals matrix techniques, they are only compatible with the when the secret distributions are over the field. So essentially what we are trying to do is to prove a randomness extraction techniques for distributions over the integers. And in order to do that, we prove a high dimensional margin lemma, which roughly says that we need the secret, the distribution of the secret being shared needs to be large far apart, and then we can prove that these two distributions are indistinguishable. And this is really the reason why our protocol required the fuse to be exponential in n square, because the determinant of the van der Waals matrix is it grows exponentially with n square. However, we expect this to be due to the proof techniques rather than an inherent barrier for our for the protocol. And with that, I will end my talk here.
Thank you very much. Do you have any questions? Please line up to the microphone.
I had a couple of questions, but maybe I'll only ask one.
Okay.
So is there like a big barrier to active security, or you just haven't really thought about it much?
Yeah, we haven't thought about it much.
Okay.
Yeah.
Thank you.
Thank you for the talk. I was wondering if the CRT-based signature, is it multiplicative? Like you can
Yes, it's so I didn't talk in the talk, but it's just like Shamir secret sharing, where when you do the local multiplication, you can think of it as a sharing of the product of the secret. So just like Shamir secret sharing, when you multiply shares, it becomes a 2t degree polynomial. There are similar structures that as long as you have 2t parties, you can also reconstruct. And if t party is still private, between t and 2t, it's a RAM scheme.
Oh, that's very nice. Thank you.
Thank you.
Quick question.
Maybe I'm missing something, but so if the total computation is just independent of n, does that mean that some parties not just like not doing any computation? Like
the total computation, the total computation is the circuit size into log f. So as we need the circuit to be larger than the.
So do you have any additive terms over there which is dependent on n?
Right, there's an additive term after that which grows with n. But if you assume
What's
there's
that additive term look like
the additive term is basically if you assume that the circuit size is larger than n, then the additive term is absorbed in this C into log f.
Okay.
Yeah.
All right. Okay. Let's thank Ping-Wan again, and let's thank all the speakers of the session.
Thank you.
This is also the end of the conference, so have a safe journey back home. Bye-bye.